recording. Just let's make sure that you can see my screen. Marco, Nico, can you see my screen?
Not yet.
I think not yet.
Okay, let's give it a second. How about now?
Okay, see, yes.
Yeah, you see the past community news?
Yes.
Yes.
Okay,
Okay.
awesome. Okay, so let me just mute you guys. Okay, welcome everybody to August meeting of the In Memory Virtual Chapter, past virtual chapter. We have today with us Marco Russo, who is going to talk about internals of VertiPaq, Power BI, and a lot of other interesting things. But before we give the stage to Marco, we have a couple of minutes of past news for you guys. So the first thing, if you don't know, the PASS Summit, which is the largest SQL Server conference in the world, is approaching quickly. It's going to be in October 27th in Seattle. And if you haven't registered yet, you still have a chance to save $150 by using the discount code that you can see on your screen at the bottom. Now, just copy it. And when you register, use this code and you'll get a $150 discount. If you haven't been to PASS, I highly recommend it. I've been going to this conference for years and it has been an important part of my career and many others. It's an amazing event to get content, learning, and hang out with the top experts in the world and Microsoft product teams. They're all going to be there. Really great experience. Highly recommended. If you haven't done it yet, go and register today. PASS doesn't offer only the summit. As you know, we offer a huge selection of virtual chapters. The one that you're attending right now is one of them. But if you go to the SQL PASS website, you can see that you will find many different virtual chapters, and probably every week you can find a different session on different topics with different virtual chapters. So here's just a select example of this month's, although all the ones that are here have already finished. If just to give you an example of the types of sessions that you can expect: index fragmentations, execution plans, synchronizing Azure, SQL DB, etc. Go to the PASS website. Almost every day you can find a meeting on one of the PASS virtual chapters. Again, all free. In addition to that, PASS also arranges SQL Saturdays. That's a full day of training in different parts of the world. You can see on your screen just an example of the upcoming SQL Saturdays. Again, it's a wonderful opportunity to go get free training, get advice from the best people in the business, and just have a lot of fun, and it's completely free. We also encourage you, if you have a SQL Saturday in your area, find out who the managers are and go volunteer. They always need more volunteers. They always need more speakers to make this event as good as we can make it. In addition to the virtual chapter, PASS offers a variety of local chapters in your region. Again, look them out. You have the URL. Go, volunteer, speak. If you can help, that would be great. There's nothing better than learning something is when you have to present on it. Believe me, that was one of the ways I learned a lot of what I know. So again, we encourage you. This is for the community, for yourself. The more people we have it, we'll have a better, stronger community. As part of this community, PASS has an annual Passion Award, which is given to volunteers who excel at what they do. If you have somebody that you know that really gives from all his heart to the community to pass, please nominate the person that you know by sending an email to the passionaward@sequelpass.org. And if if there's a committee that sits every year, looks at all those emails, checks out the references, and then a single person will be awarded the Passion Award winner. So as I mentioned, stay involved, volunteer, join us on LinkedIn, Facebook, Twitter, Pass. You believe me, for a little bit of involvement, you're going to make your career a better one in general. So without further ado, let's go back to Marco to get what you came here for. So let's make Marco the presenter, and then I can mute myself. And
Okay, can you see the screen? I don't hear you anymore. Hello? I suppose yes. Can you confirm you see the screen? Sorry.
yes, I can see the screen. Sorry,
In the
I
chat window, maybe?
muted myself.
Okay.
Yes.
Okay. Okay. Okay, I can start. Welcome, my name is Marco Russo, and the topic today is the xVelocity in-memory engine, also known as VertiPaq, which is the engine for Power Pivot, Power BI, and Analysis Services Tabular. So just before starting, a very quick introduction about me. I'm one of the founders of SQLBI.com, where you can find many articles and tools for producing business intelligence solutions with Microsoft technologies. I wrote a number of books, and just in these days we are completing the review of the definitive guide to DAX, which is the one that you see on the bottom left. It will be on the shelf early in early October, probably. So just to understand what is the topic of today. When you run a query to Power Pivot, to Power BI, or to Analysis Services Tabular, regardless of the query that you send, you have an architecture that can answer this query through two different technologies. One is the in-memory analytics engine, which is the topic of today, that is based on the VertiPaq storage, the one that is highlighted now. The VertiPaq storage is a copy of the data that you define in the data model of the tabular model, but this is a copy of the data that is stored somewhere else, on SQL Server, on the web, on Excel, on any other data source. Regardless of that, VertiPaq has a copy of data in memory. So this is the reason why it is called an in-memory technology. We also have another option today in Analysis Services Tabular, but also when you use the Power BI service. If you use, for example, in Power BI the SQL Azure Data Warehouse, the query is converted into a SQL query in real time. So there is no copy of data in memory. The technology that is used is called direct query, and this technology is not part of the discussion today. So we will only cover the in-memory mode, which today has the full power of DAX, because all the functions are supported, whereas direct query, at least in the current release, does not support all the DAX functions. So the idea is to illustrate how xVelocity stores the data, how we can monitor the usage of the memory, and what are the best practices in using this technology, and we will take a look at a few possible optimizations. I will try to keep as more time as possible also for some Q&A at the end. So I will not try. I will try to compress a little bit the content. That, of course, it could be very long. This could require 2 hours to see in detail every single aspect. But I think that to get an idea, this introduction would be very good. So as I said, the xVelocity in-memory technology is a technology that is based on the definition of a model that is always similar to a relational model. So we have tables and relationships. However, the way these data are stored is different than a traditional relational database. And let's see why. A traditional database like SQL Server, Oracle, Access are databases that are based on a row storage layout. Fundamentally, this means that the data is stored row by row. For example, imagine you have a table of customers and you have to store this data on your hard drive, for example, on any storage. So regardless of the storage, we are used to think that all the data that belongs to the same row are in a contiguous area of disk or of memory. For example, SQL Server stores data grouping as many rows as possible in a page. The page is a single unit of I/O of SQL Server, which is 8 kilobytes, but other databases have a very similar approach. So you can imagine that SQL Server stores as many rows as possible in this page, and when there is no more space for a new row, a new page is allocated. So the result of this allocation strategy is that when you want to get the data from the same row, you will get this data in the same page. So getting data for a row has the cost of a single I/O operation. However, when you have to sum the value of a column, even if you have to access only to one column of a long row that has many columns, you have to read the entire row from your I/O subsystem. And this could be more expensive than getting the data from a smaller structure. When you create an index in SQL Server, you fundamentally create a copy of the same table that has a lower number of columns. In this way, the density, so the number of rows for each page allocated by SQL Server, is higher. And having a higher density means being more efficient during the scan of a table, especially when you cannot rely on the sort order of the index. However, this is the way we are used to think when we design a database in SQL Server, but also in Oracle, in Access, and so on. So there is nothing special here. When we think about VertiPaq or the xVelocity memory analytical engine, when we think about DAX, we usually have another approach, which is a column-oriented database. Instead of storing data row by row, we will store the same table in a different way, column by column. Just as an exercise for your mind, imagine that every column is one file, a different file in your storage. This means that in a contiguous area of space in your storage, you have all the values of all the rows for just that column. This approach makes it very fast to sum or to calculate the average of the values that you have in a column of a table, because you have to pay the cost of reading only that particular column. The number of I/O operation is much lower. Now, when you think about this in memory, because you know VertiPaq works in memory, so you may think, why I have to be concerned about the location of the data when my data is in memory? Well, the reality is that even your random access memory does not have the same time to access data if the data are in a contiguous area of memory or not. So fundamentally, doing a scan of a sequential array in memory is usually faster, much faster, than getting one integer value from every random position or different position in memory. Because in reality, the random access memory has different time of access because of the cache that you have in a CPU. For this reason, there is a particular advantage in storing the data in this way also in memory. So you can imagine that every column is an array of data that has all the values of that column for all the rows. Now, this approach makes accessing to all the values of one row, particularly expensive because you have to access to many different structures. However, we are interested in doing analysis on data, so we usually group data and we usually have to get only a few columns of the tables that we have. So this is the approach of the VertiPaq engine. Without having any index, any duplicated structure that contains more data than necessary, by just scanning many times if necessary, these very efficient structures and very compact structures in memory, the engine provides very good performance. Now, this is the difference between the column storage and the row storage. Fundamentally, the column storage made a trade between CPU and I/O. We have more CPU consumption to prepare data, to process data, because we have to split the data across different columns and do the compression that we will see in a moment. But we, in this way, have a lower number of I/O operation. And since the CPU is faster than the I/O, usually, this can get us an advantage. As I said, data are not stored as is in memory. There is some compression. And the algorithms used by the xVelocity engine are very complex. But we can describe the most important and most relevant algorithms in a descriptive way that can be helpful to you to understand how to prepare data in a better way for this engine. There are two main techniques used. The first is run length encoding. With this technique, what happens? Imagine that you have a table in which the first column has Q1, Q2, and so on. Especially if the table has the rows sorted by quarter, what you will see is that Q1 is repeated in many contiguous rows. When this happens, the run length encoding, instead of storing a duplication of the data, store the same information in a different structure, where the value Q1 is stored in an array that has 3 values. The value that you want to represent, the row where this value starts, and how many times this value is repeated. Now, if you sorted the entire table by quarter, you will have only 4 rows here. And even if you have more space for each row, it is much more compacted than the original structure. And this compression does not produce slower scan time. If I want to access to a certain row in this structure, it's very simple to scan this array and to find the position that certainly include that value. However, if you sort a table by quarter, you cannot also have the optimal order for the other columns. So the product ID will have 1, 2, and then again 1, 2, and so on. Because when you reach the quarter 2, you will have again other products that you have already seen in quarter 1. However, usually you may have many duplicated values, and when the run length encoding produces a smaller structure, the engine automatically adopts this compression and stores data in this way. However, it may happen that you have a column that has data that cannot be compressed in this way, because the compression will produce a larger structure than the original one. When this happens, the engine automatically uses the original encoding without applying the run length encoding optimization. Now, you can imagine that the sort order of the table is a sensitive information for this type of compression. However, the engine tries to sort the data when you process the table so that it finds the optimal sort order, or at least the best it can. In fact, there are a few possible optimization on very large databases in Tabular where you can define how much time the engine is allowed to spend trying to sort the data in different way in order to find a better compression. So this is only the first optimization that is made by VertiPaq. The second one is the dictionary encoding. What does it mean? In a column, you might have strings or numbers. It doesn't matter. If the column has a certain number of values, instead of storing this value that could be duplicated across different rows, even if not contiguous, the engine creates a dictionary with the list of unique values for that column. And it stores just an index, an integer value that is the index to this dictionary. However, it does not require an index of 32 bits, for example. The index only requires the minimum number of bits to represent the position of this element in the dictionary. So in case your dictionary has only 4 values, because you have quarter 1, 2, 3, 4, only 4 unique values are present in the dictionary, then you know that the encoding will use only 2 bits, which means that even without any other compression, in 1 byte, you can store 4 rows. And as you can imagine, this is already 75% saving in storage space for this type of column. Of course, the two techniques are combined together, and you might have both dictionary encoding and run length encoding for each column in your data model. So this is what we have in the xVelocity store. I use xVelocity, but I also use VertiPaq because the internal name of the engine is VertiPaq, but the marketing name is xVelocity. However, when you use the SQL profiler, for example, you will only see VertiPaq as a name and not xVelocity. So these are the two techniques that we have, and these techniques are automatically used. You don't have to do anything else. However, knowing that these techniques exist may help you preparing data in order to optimize the amount of memory that your model will require. In fact, fundamentally, the fact that we have this compression usually provide around we can save 90%. We have a 10-star compression, so around 90% of space saved. So imagine you have a SQL Server database that has 100 megabytes of data without index, just the data. You can imagine that your compressed storage will require around 10, 15 megabytes. This is my experience. Maybe not 10, but 8 is a very common number. In reality, you can achieve a better compression or a worse compression depending on what is the distribution of the data and how many unique values you have in the columns of your data model. So you can affect the size of the dictionary, you can affect the probability that contiguous rows have the same value, and so you can affect the run length encoding efficiency and the number of bits that maps the dictionary by including in your data model columns that have a high number of unique values or not. So this is the most important thing that you have to remember. The number of unique values in a column is much more important than just the number of rows in a table. So we are used, especially if you are used to a traditional database, you are used to think about be careful at the data type, be careful at how many characters you put in a string. Here it doesn't matter. What is matter is how many unique strings you have in a column. If you want to repeat a very long sentence 1 million of times, you will pay a very small price for that. But if you have a short word of 10 bytes, 10 characters, and each row has a different value, this is much more expensive in this type of database. Now, when the engine reads the data and creates the copy in memory of the data, the engine has to sort the data and prepare data and do the compression. If the table is small, the engine works with the entire table. But in reality, the engine works by segment, where the segment size is by default 1 million of rows in Power Pivot and 8 million of rows in Analysis Services. What does it mean? If you have a table that has 100 million rows, the engine will read 8 million rows at a time and will do the compression. So 8 million rows, compress and store. 8 million rows, compress and store. With Power Pivot, this size is just 1 million, because usually Power Pivot runs on machines that have a smaller amount of memory. And you can imagine that in order to do the compression, the engine has to read in memory, uncompress the data, try to sort the data in different ways, and find the better compression. So it requires a lot of memory just to process the data. There are a few other details. The bit sizing of the dictionary is made at the segment level, which means that on a very large table, doing a minimal sort order for certain columns that have a low number of unique values may provide a better compression too, because you reduce the number of unique values for each segment. And this is important to the number of bits for the reference in the dictionary for each segment. This information is available in the data management view that I'm going to speak about very soon. So fundamentally, how much memory my model requires depends on the number of columns, the number of unique values that you have in each column, then of course the data type and the number of rows. But in terms of importance, the cardinality, the number of unique values for each column is much more important than anything else. So it's hard to forecast what will be the size of a database without having the real data and without doing some analysis. It is much simpler to see what is the usage made by the data model in your case after you process the data, and we will see this in a few minutes with the data management views. Now, the memory is used to store data, but also to run the query. Sometimes running a query does not require more memory, but other times it may require more memory. The reason for that is the materialization. What is the materialization? Sometimes the engine has to create a sort of temporary tables, and the temporary tables in memory are uncompressed, which means that you may have a very compressed database in memory, but in case you need to uncompress that, it will require a lot of RAM. What does it mean? Let me explain you this concept by looking at this example made with a, a special SQL language that in reality does not exist, but just to avoid the complexity of a new language like DAX. Imagine that you run SQL on Tabular. So in Tabular, your product ID, store ID, customer ID, price are 4 different structures compressed with the techniques that you have seen before. But in reality, when you run this query, you run a SQL query that want to aggregate the price, want to sum the price column by customer ID, filtering only a certain product and a certain store ID. So this query has to do what? In case of early materialization. What is early materialization? With early materialization, we create in memory as soon as possible a copy of the data that represent the rows that we want to analyze, just with the columns that we have. By building this table in memory, we start from a compressed version of the table, and we obtain a table that expand in memory all the duplication that you tried to compress before. On top of this structure in memory, we apply the where condition that only filters a few rows, we apply the projection that only gets a few columns, and we apply the group operation that reduces the result to a single row. However, in order to obtain one row, we had to create in memory 4 rows, maybe 4 million rows, imagine. That is very expensive because these rows will be created in an uncompressed way. However, in the ideal case, we have late materialization. So we will obtain the materialization of the result as late as possible, just at the end, with the minimum number of rows. This means that the engine has to be smart enough to apply the filter and aggregation, possibly by just creating indexes, bitmap indexes, on top of the existing in-memory structures. For example, imagine you have the same structure as before. The where condition simply generates a sort of bitmap index, a sort of 1 and 0 corresponding to the same position of the rows of the table. And this structure that can be compressed as well in memory is very inexpensive because you have 1 bit for each row. You do not have to duplicate the data. The end operation between bitmap indexes is something that a CPU can do in a very fast way. And this bitmap index is used to filter the data during the scan of the other columns. In this way, the materialization is the minimal as possible, and in this way, we do not have to spend too much memory for that. So the materialization problem is something that we can see in practice in this way. I have a small database here that has a numbers table. The numbers table is a table that has 100 million rows. The number that you see is the number of rows of the numbers table. The numbers table is a table that has 2 columns, num1 and num2. If I try to count, so I run the distinct count, the number of unique values of each column, you can see that the first one has, let me run this, the first one has 10,001 values, and the second one has 10,000 values. So fundamentally, I created a table that has 100 million rows and has all the combinations between the numbers between 1 and 10,000. We have all the combinations in this way. So this operation, as you see, scanning a table that has this number of rows is very quick, does not require too much time. But if I run this query enforces the materialization. This is a trick that I do. I know that this instruction in this case will produce a materialization, will force the engine to materialize the entire table in memory. And when you do that, the first thing that you notice is that instead of getting an answer very quickly, I'm waiting. I can wait for minutes now, and if I show you my task manager, you will see that Excel is increasing the memory here. As you see, analysis services in this case, you can see here, I have this one. I have already 10 gigabytes used, and this is going up. So it is spending CPU and memory just to materialize this intermediate table that is really unnecessary. This is an extreme case. I'm stopping this to not exhaust the memory, but it's just to show that the materialization issue is what you likely have when you have to wait too much for a query in your data model. This is an extreme example. I hope you will not have this in your case, but this is just an example, an extreme example of what can happen when materialization is in place. So, okay, how can we know how the data have been stored and how the memory is used in your model? Well, we have a few data management views that can provide us a few information. And for example, here I have prepared a couple of this just to show you that by running this query, I can see a few information about the schema rows. That is just how the data has been defined. But this data management view provide me other information about the memory cost of each object. However, reading data in this way could be particularly, expensive in terms of time required. So for this reason, we recently tried to create a model, a Power Pivot data model actually, that access to the existing data management view and provides you information in a very detailed way. You can download this workbook from this URL, and there is also an article that explains in more detail how to read it. I just want to show you what are the type of information that I can obtain from a data model. For example, this is the Contoso data model, and you can immediately see, in this representation, you can see the data of tables, and then for each table you can see the columns. For each table, I see here the space required. So the table size is 94 megabytes in this case, and I see that the amount of data spent in the data itself is just in the dictionary, in the hierarchies, in the relationships. I have all this detail of information. And this could be very important because, as you can see, in certain tables, the dictionary is more expensive than just the data, like the customer table. However, in other tables, like the sales table in this case, we have 12 million rows, and we spent 94 megabytes for that. In which columns? What are the columns that are more expensive? There is another view that can show you this data. Remember, these are the data that are in the data management view. We just collected this data in a Power Pivot model, and we organize the data in a more readable way. And just to show you a few more details, we also have hierarchies, relationships. But for example, if I want to know which kind of compression has been used, how many bits have been used for each column, I have this information too. I can see for every column, in every detail, the type of compression used, and so on. And based on this information, you may decide, for example, that, oh, this column, I don't need this column, I can remove this column, I will save a lot of RAM. Or you may locate why this column has a high number of unique values. We can lower it. Now, it is not the case of this example, but in certain example, you may realize that a column has a very high cost because it has a very high cardinality, and you don't need this column. So the best way to optimize a model is to remove columns. I just quickly show another example. This is a 4 gigabytes database. Sorry, not a 4 billion rows database that requires almost 14 gigabytes. And as you see, we use exactly the same tools in order to understand where we spend our memory. And you can realize here where we are spending more. In reality, this is an already optimized data model. But as I say, this is a very effective tool that will help you understanding how to improve the compression of your model. Now, when you have a data model, you also have relationships. Now, relationships between tables are usually cheap in terms of memory. But there is an important information that may affect performance, and is the cost of the relationship in terms of cardinality. So how many unique values you have for a relationship. And this cost depends on the number of unique values that you have in a column. For example, here you can see that in this, let me get the other model, sorry. In this model, we have a table that has 4 billion rows, a lot of rows. This table is a table that has many relationships with other tables. However, the relationships do not have a high cost. The cost of a relationship, even in the audience table, which is the 4 billion rows table, does not depend on the number of rows in the table, but on the number of unique values that you have in that column. So if you create a relationship between two tables using a column that has 10 million unique values, you will see slower performances. And in this view, you can easily identify that, oh, this relationship could be too expensive. So in this article, you will find a more detailed explanation of how to optimize relationships in your data model. Another thing that you can do is reducing the dictionary size. Since the compression requires a dictionary, if we lower the number of unique values in a column, the better. Now, if you have a column that has date and time, the first thing that you should do, split this column into 2 columns, because 2 columns have a lower cost than 1 in this case, because in date you will have only the dates, in time only the time, and possibly only hour and minutes without the seconds. So you reduce the number of unique values. If you have a floating point value, you may round this value, because remember, also floating point value is stored in a dictionary. So every minimal change in a floating point value requires a new place in the dictionary. If you have money, you don't want to lose anything, I know, but you will use probably the currency data type. when you have a floating point value, for example, you measure the temperature that you collected from a sensor, you might have 5, 7, 10 decimal points, but in reality you know that only the first one is relevant. Just round it and save a lot of space, if you can, and if this does not lose important information for your data model, of course. The most efficient way to improve the compression is, of course, reducing the number of columns, removing the columns that are not useful, and also reducing the number of calculated columns. If you create many calculated columns to split the calculation in several steps, that's fine during the development, but when you go in production, especially in a large table, try to reduce the number of calculated columns, because each calculated column will cost memory. Another optimization is the one that you have to do when you, for example, have a unique ID in a fact table. Imagine sales and you have the invoice ID. You might have many more invoice ID than anything else, or transaction ID. If you can remove this column, the better. But if you have to keep this column in the data model because the user, oh, I want to be able to drill through and to see the original transaction number, that's fine. But consider that if you split this number into two numbers, you may save a lot of memory. Then, of course, you will lose the ability to do the distinct count on that column. But if you don't need this feature, then splitting the column could be an efficient way. For example, if you have a 100 million of transactions, like in my previous numbers table, I had all the numbers between 1 and 100 million. Instead of storing with just one column with 100 million of unique values, I stored two columns with 10,000 unique values in each column. This will save memory, but does not necessarily improve the performance. Remember this, with the latest builds of analysis services, or also with Power BI and Power Pivot, having a smaller amount of memory usually improves the performance. But in this particular case, if you have, in any case, to evaluate 100 million rows, storing an ID into two columns will not save too much time during the scan. With older build of analysis services, there was a performance advantage in doing this. Today, you just save memory, which can be still important. So, regarding of when you create a data model and you have to decide what you want to store in the cube, in the data model. I use the cube word, but in this case, cube is not appropriate. Is the model. So, if you have a table that has the sales, the sales transaction, well, you have order ID, product ID. Maybe you want to store this information because these are the foreign key to other tables, and you want to keep them. Then you have quantity, price, discount, and usually these columns have a low number of distinct values. If you think about your products and the number of different quantities you have in your model, usually there are not too many unique values. However, the sales amount usually, since the sales amount is quantity multiplied by price, usually the number of unique values here is higher than the others. Now, if you consider that the sales amount value can be evaluated at query time, you may think that it's crazy to calculate the product of quantity price when you query the model, but in reality, you may find that this is much faster than storing the value as a calculated and pre-computed value. This, in reality, this depends. It depends on the hardware, on the version of analysis services or Power Pivot and so on. But for medium and small models, usually I prefer to store quantity and price because the difference in performance is not measurable, but you will save a lot of memory. Only for very large data models, billion of rows, I consider storing the sales amount value because the difference in performance may have some benefit if I use that column instead of doing the multiplication between quantity and price. But remember, 10 million rows, 50 million rows, no ways. Use quantity and price and save more memory. It is usually better. So the difference in size could be really big. On older version, depending on the calculation that you have to do, storing separate columns could be better. In a case with 4 billion rows, we moved the column from 9 gigabyte and a query that required 13 seconds. We moved this down to 3 seconds, reducing the size to, if I remember, only 1 or 2 gigabytes. Just because we removed a column that was expensive. So I try to give you a general introduction of xVelocity in memory database. What is important is to remember that you work with a compression and data in memory without any index. So every time you run a query, the engine has to scan the columns that are involved in the query and has to find the values that are relevant for the calculation. So having a better compression means that the time required to scan that column is smaller, and this means faster performance for your query. When you process the data are processed segment by segment, and the segment size can be adjusted in analysis services. In fact, the default is larger, and usually a larger window for the segment means better compression, because you can, the engine can sort the data and range the data in a better way. In terms of segmentation, having many segments also helps the parallelization of the queries. So in a larger table, having many segments means that being able to use more cores to do the calculation. However, having less than 1 or 2 million rows in a segment is usually not effective, because it's a too low number of rows in order to see benefits in parallelization of the query. So if you have any question, I try to keep time for the questions, and so I have 10 minutes to get your question now. I don't know how it works. I think you have to write, or the moderator has to read them.
Yes, correct, Marco. If you want to ask a question, you can use the questions tab on the control panel of the GoToMeeting. But I see that we have no questions, which means you did a very good job, Marco.
Thank you very much. I think that there are questions, just maybe they will arise over time. Remember, you can write me at marco@sqlbi.com if you have any question, and I will be happy to answer in my spare time, maybe not immediately, but usually I always find the time.
Yeah. Okay, people, last chance. If you have any questions for Marco, this is the time. If not, then we will adjourn today's meeting. So we do have a comment from Mark Umbach. Very interesting, but complicated.
Well, in reality, the good thing is that you don't have to worry about this. I mean, all the complexity is hidden. The problem is, if you have a model and you want to optimize the model, you say, oh, this workbook in Power Pivot is 20 megabytes. Can I optimize it? That's the point. If you know how this works, you may be able to optimize the model without even measuring anything, because you can immediately realize, oh, this column is not necessary, this column has many unique values. You can remove the data that you don't need, and then yes, when you say, I want to keep this data, but I want to optimize the space for the data that I want to use, then of course you have to learn some technique. I think that looking at our articles and books, you will find much, longer discussion about the techniques, but also just looking at the articles and the blog, you will find a lot of interesting points.
Yes, thank you. Also, Ashish asks when I can see a replay of this webinar. So, Marco, just a reminder, send me the PowerPoint, and I will upload it either today or tomorrow with the recording.
Okay. I will send you just after the the end of the meeting. I have seen a question about multiple developers environment and model sharing. This is a very bad story. I mean, I imagine that you reference to analysis services tabular is not related to VertiPaq, of course. The problem is that the model in the current version of analysis services is just one single file in XML, which is very bad for also having a single repository where you want to merge different changes. Next release of analysis services will be much better, but you have to wait for the CTP3, not the CTP2 that you have now. In the CTP3, there will be some good news for that.
Okay. Aaron Grossman says thank you.
Nice. Thank you, too. Thank you for attending.
Okay, so I think we are done. So thank you again,
Okay.
everybody, for joining us today. We hope to see you again in next month's meeting. And thank you again, Marco, for a wonderful presentation. I'm going to stop the recording now.